We have poster presentations.
Thank you.
So
Dario. So we start with Dario. Each lightning talk is for 3 minutes.
For 2 seconds, I'll keep in my hands. Okay, my name is Dario Fadda, and I work in the Roman group at the Space Telescope Institute. So my poster presents a few tools that have been developed at the Institute to essentially help users to do their proposals in an optimal way. So I divided this in 3 parts. The first parts consist in quick look tools. The first is the wrist, which helps you to do some time estimates for observation. And the second one is the footprint viewer, which helps to put the footprint of the WFI, so the wide field instrument, on a field. These two are offered as Jupyter notebooks, so are pretty easy to install and to use. The second one is the proposal tools, so Pangaea and APT. Whoever have already done some HST or JWST proposals probably know them. These have been adapted to essentially take into account the WFI features. Mainly it's the big field of view, so the possibility of doing big surveys. And the last part is the simulation tools, which essentially helps you to simulate some observation. First is the WebPSF, so which I forgot the F, I see. The WebPSF that essentially give you the possibility of creating PSFs in any location of the WFI. Then we have the steps, which I think has been used by another poster that is out there. And this can give you the possibility to do biggest scenarios where Pangaea allows you only to put like 5 sources at the maximum. Steps allows you to put a lot of more stars and galaxies. And finally, there is another tool which is called Roman iSim, which will be a version of GalSim for Roman, so taking into account all the particularity of the instrument, which for the moment is only available in GitHub, but will essentially be available soon and is in course in development. Thank you.
Dion.
Hello, my name is Matt. I'm a grad student from Duke University, and my poster is about continuum level redshift estimation for the Roman Halide-2 spectroscopy survey. And, so the motivation behind this project is that red crescent galaxies is important for cosmology studies, especially for example, for galaxy clustering and also for galaxy-galaxy lensing. And so given the infrared range that we can probe by Roman, we can have the possibility of that we can probe more high Z LRGs from Roman. And then this is especially exciting because we can actually explore the possibility of combining combined surveys such as the Roman LST with Roman, so that we can potentially have a more complete sample of red galaxies for cosmology analysis in the future. And then the primary goal of this project is trying to quantify the capability of Roman's spectroscopy survey, particularly the GRISM component on understanding how well we can measure the redshift for those red galaxies. So despite that, they are not the primary targets for such as emission galaxies for Roman, we can still measure their redshift because of their spectral features. For example, the 4000 extra break in the spectra. So what we're doing is we simulate our own Roman GRISM simulation image based on the reference survey parameters. So we have the 4 position angles and also the default exposure time is suggested in the reference survey. And for each of the red galaxies we have in the simulation, we perform spectral extraction and also redshift estimates on every individual red galaxies we have. And then, so the results, preliminary results we have is the redshift efficiency curve that we use to quantify our performance. So what is shown is that this showing the fraction of red galaxies in our simulation that is expected to have pretty accurate and ideal optimal redshift estimations as a function of magnitude as in our simulations. So this is all for the red galaxies we have in the simulations greater than redshift of 1. So so we did this for different scenarios. So first of all, we tried to do it on different exposure times. So as shown here on the left figure, the blue line is what the baseline or the reference survey we expected to have given the current survey strategy. And we also explored that within the current survey strategy, how does the number of exposures impact the results? Because we know that given the current dithering and pattern that we have for Roman, all the galaxies might not have all the exposures that I expect to have. So some galaxies will have less number of exposures. So we also explored that in our project. So for the current status, we're wrapping up the project, and so that's the reason why I'm here going to giving a presentation, and also hoping that the outcome of this project can also give some additional information on people deciding the final strategy of the Highlight 2 survey. And thank you. And I'll be around, and if you have any questions, you can just come to me. And I'll be around the poster for the coffee break. Yeah, thank you.
Thank you. The last one is Daisuke Suzuki, who is online, I think. So Daisuke, if you can unmute yourself.
Yep. Can you hear me?
You can share the screen. Let me stop just in case.
Okay. Oh. Oops. Okay, maybe I will start with this. So you can see the slide, right? Okay. All right, so I'm Daisuke Suzuki from Osaka University. My poster is synergy between PRIME and Roman. So PRIME telescope is a new near-infrared telescope built in 2022 at Sutherland Observatory in South Africa to conduct a dedicated H-band micro-lensing planet survey towards the galactic center, including the Roman field. So it is a 1.8 meter telescope, and its primary instrument is wide field imager, the PrimeCam, which is using the 4 H4RG10 detectors. And the field of view is 1.45 square degree, and it has a near-infrared filters, GYJH, and 3 narrowband filters. So the operation is done by Osaka University team, and the time allocation is like this. So the hardware is ready. So we started the near-infrared microlensing survey this year. So this image is tiled prime H-band images towards the galactic center. The green square is showing the one field of view of prime, and black lines are detector gaps. And these red rectangles are optical Moore microlensing survey field. So here I summarize the Roman prime synergies, and these first 3 topics are related only to the Roman microlensing survey. So here the last topic is the detector characterization, and this is related to everyone to use the Roman WFY. So here I focus on this topic. So this okay. So these 2 images are the same ramp images from the prime telescope, but using different non-linearity correction method. So unfortunately, prime detectors, H4RGs, are operated at 170 Kelvin. It is very high temperature than expected, and which leads to many hot pixels in the detector. And this hot pixel has a high dark current, and yeah, so the conventional JWST nonlinearity correction method cannot work well. So as we can see in the left image, there is a cross-hatching pattern. So we developed the dark current model within the nonlinearity correction framework. And the right image is a new method, which works well even for the hot pixels. So which might be useful for to understand the Roman detectors if they have hot pixels. So please come to my poster. And unfortunately, I'm in Japan, so Takahiro Sumi and Naoki Koshimoto, they should be around there. And so please find them and ask them about the Prime telescope. Thank you.